The first question is about AlCl3 and AlCl6. AlCl3, what is that? Is that well, aluminum is typically thought of as a metal, non-metal, semi-metal. Metal. And so it's a metal plus a non-metal, which would make it an ionic compound. So that's the way we typically analyze it. But actually, aluminum is right on the border between metals and non-metals. And so it actually has properties of non-metals too. And so aluminum is what we call semi-metal. And so this would be a semi-metal. Semi-metal, non-metal is kind of starting to transition from, the more ionic bonding to the more covalent bonding. And so, well, anyway, continuing, actually these pens aren't that great either. Continuing with this, if I have Al3O plus and 6 Cl minuses, what can happen is that the aluminum just gets surrounded and packed by the aluminum is, what do you notice about aluminum? One thing that you might notice is its high charge on small size. So high charge, small size, these chlorines are going to be so attracted to it, it actually bonds to it, and 6 of these can bond to it, like this, to form an octahedral arrangement of chlorine atom. But this whole thing is going to carry a charge now. This whole thing carries a -3 charge. And this is what we call Lewis acid-base reaction. Lewis acid-base reaction. And these species are unusual in Chem 1A. These are called complexes. And complexes are going to be discussed in Chem 1B. And so you don't have to worry about complexes for this. So AlCl3 is fine, but AlCl6 is, just wait on that until talk about those.
Professor?
Uh-huh.
When do you show the one that has the brackets and the one that we actually...
Well, whenever you have an ion,
But isn't that like a metal and non-metal?
whenever you have an ion in a Lewis structure, you show the bracket, even if there's no valence electron. And so if I want to show the Lewis structure for this, I would use a square bracket. And then this, to show the Lewis structure, I need the octet electrons here. And so what's happening is, this is a Lewis acid-base reaction, which the electrons are being donated. Remember, electron donor, electron pair acceptor, Lewis acid-base reaction.
But isn't aluminum losing the electrons?
Mm-hmm. Well, aluminum's already lost the electrons.
Wait, so that's different. So when it's ionic, is when we show the brackets, right?
Here, you could do this reaction like this: aluminum plus chlorine gas. This is a redox reaction. The elements. What would you expect to form? You'd expect to form AlCl3. Here, aluminum would be losing electrons to chlorine. This is not a. This looks like a metathesis. If we formed AlCl3, it would be a metathesis, ion combination. But when we go to AlCl6, 3 minus, then it's a Lewis acid-base reaction, not a simple metathesis. Okay. Lewis acid-base reactions are more complex, so we look at those in Chem 1B rather than in Chem 1A. So let's not worry about it now. Although it's something you got to keep in mind, when you're thinking about chemical reactions, there's acid-base, but we've been focusing only on Bronsted acid-base. Much easier to deal with. All right, Adrian, you had a question too?
Yeah, I got, when you're showing the hybrid, sometimes you show like a dash bond, and then sometimes you show the lone pairs.
Dash?
Yeah. So when do we...
When it's delocalized, you show it as dash. Delocalized means spread out over the structure. You show dash. When it's localized, then you show it as solid. Whatever you do. So delocalized, that you have the funny kind of smeared out, the fog, right? The fog spreads out, and so that's the fog of the electron cloud. We'll look at an example today. I'll do some more. in a minute. But did you have another question?
Yeah, I do.
Okay.
Why doesn't aluminum change colors when it's heated up?
Why doesn't aluminum change colors when you like vaporize it?
Yeah.
Well, aluminum is, if you look at the electron configuration for aluminum, Al3 plus, Al3 plus, it's, yeah, 1s2, 2s2, 2p6. And so basically, if it doesn't change color, then that means the gap, let's say between the two n equals 2 and the n equals 3 orbitals is too big. And that gap being too big is in the UV. Or, it could be other things. Or the gap is too small, so it's in the infrared. And the next gap up is too big, it's in the UV. And so it just so happens that where the gap lies, in this case, I'd expect the gap to be too big, because what do you notice about this? It's got the filled shell configuration, the same as neon. It's isoelectronic with neon, so that filled shell should be additional stability, which means it's probably the gap is too big. It just so happens, you measure it and see what the gaps are. And then, so some of these things, when you heat them up, are colored, like a lot of them actually, but some of them aren't. So colored. Why? Why is not necessarily. Sorry, it's not necessarily why. It's just we observe and then try to describe that at a theoretical or fundamental level, and that's it. So one question is, why is when sodium's excited, it's yellow or orange, yellow-orange, right? Well, people will say it's because electron transition. Then somebody asks, why? Because electron transition is a yellow-orange. Why isn't it blue-green? Oh, it's because of the gap. Well, why is the gap like that? It just is, depending on how things are. And so scientists just try to describe, they didn't pick, why did sodium choose yellow, orange, just is. All right.
Yeah, I have a last question. It's a statement that I wrote that you said, but I was trying to understand it, but I couldn't. It says that fluorine has a lower attraction than chlorine. I don't know if I wrote it wrong, but it says that fluorine has a lower attraction than chlorine.
No, that's wrong.
But it has more space to accommodate the other.
No. Chlorine has a lower attraction than fluorine.
That's what I was.
Yes,
okay.
chlorine has a lower attraction than fluorine.
And what is that it has more space to accommodate?
Because it has a bigger orbital.
So chlorine has a lower attraction than fluorine.
Yeah.
But it has more space to accommodate?
Right, and so its electron affinity is higher because it can accommodate.
So chlorine does?
Yes, chlorine. The chlorine can more easily accommodate an extra electron.
That's what I thought.
Well, how do we use it? Like I said, we just use electron affinities just for calculations. But if we're thinking about an oxidizer, which one's a better oxidizer, fluorine or chlorine? Fluorine. And so, and the energy difference, is it all that huge? No, it's not that big of a difference. So fluorine's going to dominate nonetheless when it comes to chemical reactivity. And so, yeah, sure, chlorine has a higher electron affinity, but that's almost kind of worthless in a way, because I mean it's worthwhile for calculations, calculate more precise, more accurate energies, but it's kind of worthless in predicting, how they behave, because fluorine is a much more powerful oxidizer than chlorine.
And my other question was, when we're doing the valence bond, and we have we have the carbon and the hydrogen is coming in.
Yes.
Like, how can we know for sure that that electron that we're pointing to is the carbon? Like, I don't know if that, in my head, I don't know.
How can we know the?
Is that we're assuming that is the electron coming in? Because how can we know precisely? We know there are two electrons in that orbital, but how can we know, okay, this electron is coming from here, and this electron is coming from here?
I mean, it's just it is arbitrary. I just pick one. I mean, you can pick it the other one. fine.
It doesn't matter?
It doesn't matter.
Because I'm getting confused, like, you know, when it's
Spin
pointing
up,
up and down.
no, all you have to remember is it doesn't matter, you know, because spin up and spin down, it's like this. If you're on the, if you went to Australia, are you upside down now? Or are you still right side up? If you go to Australia,
Same.
or let's say one person's on the North Pole, the other person's on the South Pole. Is the person on the South Pole upside down, or is the person on the North Pole upside down? Which one is upside down? You know, it actually doesn't matter because the spins are just that. You know, right side up. If I was on the South Pole, this would look upside down, right? Versus on the North Pole, it looks right side up. So it doesn't matter, you know. The spin, you just pick one and make the other one opposite. And if I pick carbon and spin down, no big deal. Then the other one must be spin up. You know, it doesn't matter.
Yeah, because my point was that in the lecture you were pointing at one, and I'm like, whoa, but how do we know that?
Oh, God, no, I'm just pointing at a electron, not a specific electron. Just one of the electrons comes from carbon, the other comes from...
Does, so like
right,
okay.
right. Unlike, well, I just erased this. In a Lewis acid base, it doesn't happen like that. In a Lewis acid base, both electrons come from chlorine to aluminum. It's not one comes from chlorine, one comes from aluminum, and they pair. When they pair up, one's got to flip. It doesn't matter which one flips. One's got to flip. Otherwise, what's violated? Pauli exclusion principle. And so they both could have been spin up, but they can't come together, spin up. When the orbitals overlap.
And when we showed the energy in the diagram and then the...
let me go back one step. It can be like this, but we call this a excited state, not the ground state. In fact, that's what I did. I use magnets to flip the spins. It takes a certain amount of energy to flip that spin. And when you flip the spin, it depends on the surrounding environment, you know, how much energy it takes, so it gives you information regarding the surrounding environment, which makes it useful in structural analysis. Okay, sorry, go ahead.
Well, what I was thinking is when we're doing the drawing and then we have the energy orbital diagram,
Yes.
do they have to agree? Like if I put this one up and they have
Yes.
it, right? So
Yeah.
if I say this is the carbon.
Right, then the carbon should be the same spin on the other. They should agree to be consistent, you know. But it doesn't matter because the carbon could have flipped the other way and then that flips the oxygen the other way in an instant time, you know.
Okay, so that's what I was
Yeah, it's just, yeah.
So you would not be like super concerned about how we point it when we read it, as long as we show it?
No, I mean, it should be consistent, but you know, let me tell you, I'm not going to have you do, I'm just going to have you do it from one atom's perspective. You know, like say the carbon, the central atom's perspective. Maybe I won't have you do the terminal. Keep it clean. You could, well, you should know. I mean, it's not that. And so if I gave you formaldehyde, I'd like you to do carbon. You know, keep it simple and just do carbon, the central atom.
So you have to draw the...
Yeah, you have to draw the orbitals.
But we don't have to show the electrons? Is that what you're saying?
No, you should show me the electron. Are you saying, okay, draw the carbons and then draw the oxygens? Something like this, maybe? And then show it from carbon's perspective and show it from oxygen's perspective. You said an energy level diagram, right? Is that what you're talking about?
And the drawing, like when you actually draw all the...
Well, the drawing is a separate thing, but yeah, you want to show it all. So let's say there's an sp3 bond here. You know, you'd show carbon, and then you'd show oxygen. So let's say this is oxygen, carbon, and carbon comes in here. And I draw an arrow pointing here because this is carbon's electron. Do you see? The same. And then I draw an arrow here showing this is oxygen's electron. Okay. That you should be consistent. We'll try to. Okay. Other questions?
Good question. For the MO theorem,
Yeah.
you're supposed to know for each orbital the joint part. Are we supposed to know what each orbital part looks like sigma pi, 2 pi, or 2s, 2 pi, 2 pi star, something like that?
So,
That's those are you draw all the things all together.
right. Right. Should you memorize the shapes of all the orbitals? Memorizing the shapes of the orbitals is helpful, you know, and thinking about the electron density map.
Yeah, that helps for the test purposes.
For the test now. In the past, I have asked people to draw the orbitals. I don't know if I did it. Did you guys look at the sample test I put up? I don't know if I did it in that. Did I ask you for the drawings of the? Okay, sometimes. That's usually like a bonus type question rather than a regular question because most people don't know the shit.
There's no bonus question.
Why, you don't want to?
I mean,
You don't want to? You don't have to, no, that's all right. You don't have to memorize all the shapes
Yeah, memorize the bonus.
of the MOs.
it's not quite fair.
You don't have to memorize.
You don't have to memorize. So, okay, other questions? Uh-huh.
What's the difference between electron affinity and electron negativity?
Electronegativity is just the attraction only for electrons. Electron affinity is attraction plus accommodation, space. You know. Which one do we use more of? In calculations, we use electron affinity, thermodynamic Hess's law type calculations. For just predicting chemical reactivity, we use electronegativity. For predicting things like how ionic a bond is, we use electronegativity. In fact, did I draw the little chart here about delta En, the difference in electronegativity and the percent ionic character? And this is how we use electronegativity. We look at the difference in electronegativity, delta En. You know, this is just a tug of war. If there's a big difference, then it's a one-way match. If the difference is minimal, then it's two-way. And then we see, a percent ionic character. 100% ionic character means, winner takes all. And so the larger the delta En, the more ionic the bond. And you can get the trend line like this. But when you look at the data, the actual data for this is all over the place. I mean, the data, you take a look at the R squared factor on here. I mean, you can see that, yes, it does follow the general trend, but sometimes there's some exceptions. Like this. And so when we look at the trend line and we look at the fit, the R squared is not going to be so great. But it loosely follows this. So some people come up with a rule. And the rule, or there's exceptions to the rule, but the rule is that if the delta En is less than 0.5, we call it nonpolar. And if it's between 0.5 and about 2.1, this is what we call polar covalent. This is rough because some people will extend this out because when you look at the data, it's all rough. These aren't hard numbers. And if it's greater than this, then we call it ionic. And so the question came up, is aluminum chloride, AlCl3, ionic or covalent? Because its borderline is, it's between, and so there's some covalent character in the bond. And, things don't have to be 100% ionic or 100% covalent. It's not always black and white, right? There's a lot of gray in this. There's some sharing and then there's some taking. And so this kind of gives us an idea. In fact, what's better than calling it nonpolar, polar, covalent, and ionic is just assign it a percent ionic You know, it's 75% ionic, 50% ionic, 5% ionic. You know, if it's 5% ionic, then it's 95% covalent, right? And so there we can look. And so there's some unusual species like lead-4, you know. Lead-4 compounds are typically covalent. Lead-2 compounds are typically ionic, you know. And so there's quite a bit of covalent character in a lot of these heavy metals here when we look at that. Okay, but the electronegativity is probably the most useful for us. The electron affinity is only when you're doing thermocalcs. All right, what else? Uh-huh.
For EA,
Uh-huh.
like EA1 versus EA2, like most of EA is thermic, sometimes EA.
Most of EAs are exothermic.
EA2 could be like endothermic.
Most EA2s are endothermic.
So how do you determine that?
You don't worry about it. Just know the trend. Actually, you don't even need to know that. You know, EA1 exo, yeah, but EA2, yeah, it's more electrons. EA3, you try to put a third electron in there, it's going to be less and less favorable. And so as you successively add more and more electrons, it's going to become less and less stable. You know, it's just like as you successively remove electrons, you know, one electron after the other, it's going to become less stable and harder to do. And so just know, EA1, EA2, EA3 gets harder. For sure, you should know something like EA1 for fluorine should be highly exothermic. Fluorine, chlorine, bromine, all those are powerful oxidizers, and they want electrons. Okay, other questions? But the thing is, you think, you know, it's always confusing because what are some powerful reducers, like lithium, right? Lithium is a powerful reducer, so you would think I1, ionization 1, would be exothermic, highly exothermic, right? Is a powerful reducer. But it turns out it's endothermic. And so we interpret that differently. We interpret this as being, well, the ionization energy is fairly low, you know, and therefore it's a good. This is why when I think about redox reactions, I don't really think about the reducers. I just think about the oxidizers. You know, the oxidizer is strong enough to take electrons. It depends on the ionization energy. Alkaline metals have very low ionization energy. Not negative, but very low. All right, other questions?
Yeah. When we're considering like electron-rich and electron-poor species,
Yes.
is it the central atom that we're looking at? Like CO2,
No.
for example?
Typically it's the central. The reason it's typically the central atom is because the terminal atoms are highly electronegative, usually. And being that, you don't normally want to give up the electrons, but not always. You know, sometimes you can pull electrons off the terminal atoms. You know. And so sometimes what we have to do is there could be electron rich and electron poor in the same. But for most of the species we encounter, that wouldn't be a bad thing to keep in mind. It's going to be the central atom that dictates the property. It's like hydrogen, you know, and chlorine and fluorine as terminals. Those aren't going to want to lose. But if you have something like iodine as a terminal atom, iodine's a big atom. It could be oxidized, even if it's not a central atom. And so, look at at electron poor and electron rich today. Okay, other questions?
What chapters in the class? What chapters in the class?
Just 9, 10, and 11.
9, 10, 11.
Yes. No 16. I want to finish 16 today and start 12.
That's going to be 4 chapters of 6.
One at a time. What?
What do we have to know for 16 these tests?
The HF, HCl, HBr, HI.
Alright. Strong.
Why is which one's the strongest and why? HI because.
The bond is so weak.
But what about polarity? HF should be more polar, so therefore shouldn't that be the strongest?
It'll attract the base better,
Yeah.
but the base can't rip it off.
Okay, good. Then that's it. That's all you need to know. Yeah. That's it. You know, in the afternoon, some people were not so happy that bit of chapter 16 I wanted to put on the test, but you know, all the arguing back and forth, you could have learned this stuff in that amount of time because it's not that much stuff, right? I think it's not that much stuff.
So what is it? We have to know HI.
HF, HBr,
HF, HCl, HBr, HI. Which one's the strongest? Look at our acid chart. HI for sure is the strongest. Yeah, but the weird thing is HI is the least polar, so why is it the strongest? Because bond energy must dominate, and so you try to give that visual about the base coming in to try to pluck off the proton. Okay. Other? Arthur had it right. Exactly. That's exactly what I want to hear for that. Okay, what else? Okay, if there are more questions, just go ahead and ask me. Let me continue with chapter 16. Those are the binary acids, like H2O. Is H2O a very strong acid? No, even though that's highly polar too. H2O is highly polar, but it's not a strong acid. Why is that? Bond strength, right. You'd expect water to be a powerful acid based on its polarity. Because what's number 2 in electronegativity? Oxygen. Oxygen is number 2. And yet it's a very weak acid. All right, let's talk about, those are the binary. So typically what do we look at first when we're considering acid strength? Bond strength. But what if the bond is the same? And so that's what we're going to look at next. Oxyacids. Oxyacids are going to have an HO. I'll just put R, HOR. There's going to be the rest of the molecule. But we're looking at this now. Now the bond is roughly the same. All oxyacids are going to have an HO bond. Right? Oxyacids HO bond, and so that means the bond strength is roughly equivalent. And then the hydrogen, this is what we call an acidic hydrogen. So let's look at some oxyacids. This is, even though it's a new pen, it's not so great. Let's try this one here. Acetic acid. Let's do it. Acetic acid is CH3COOH. This is the COOH group. This is carboxylic acid. We talked about that a long time ago. What's the hybridization on carbon here?
SP3. No, SP2. SP3.
Just S.
Oh, just S.
It's unhybridized. I mean, have you gotten good at these?
I think so. It's just like, it's hard to draw it. It's so
It's okay.
to visualize it. It's so like, I don't know.
Get better
Like, especially like when you do side view and then you do top view. And
Well, this one, you know, if I gave acetic acid, I wouldn't expect you to do side view and top view. Just one view.
So when you said that you would only ask for one,
Well, here, you just try to draw as much in the plane as possible. So 2 in the plane, 1 coming out, 1 going in, right? Okay, so this is the sp3, so we have hydrogen here, and hydrogen here.
and then the electron.
Yeah, then we put in the electron.
And we name it, right? It said SP3.
Yeah, we name it.
And we named the bonds as well, right?
Yeah, we name the bond. So
SP3 hydrogen.
sp3s sigma. sp3s sigma. In fact, all these are the same. Except this one is going to be a little different. This is going to be carbon to carbon. And what was the hybridization on this carbon? sp2. And so we got to draw the sp2 orbitals out. Yeah. You know what I'm going to do is I'm going to make it a little easier for me. I'm going to put the oxygen here, and then I'm going to put the double bonded oxygen here. The double bonded oxygen was what? sp2. So let's make this sp2 here. All right, so this bond here is going to be a sp3 sigma. Sigma.
So that's all we do for one?
Yeah. And then over here we got to have a sp2 sigma, and then a pp pi. So let me do the pp pi here. How should I draw the p orbital? Yeah. So this is called the top view here. So here's a p, here's a p. And so I'll just draw some lines connecting the p. So this is a pp pi bond. Put the electron here and electron here. And then what do I have on this oxygen down here? I have 2 lone pairs, right? And then I have an oxygen up here, which is sp3. Right. And so I'm going to form an sp2, sp3 sigma bond. What's this oxygen bonded to? Yeah, this oxygen is bonded to a hydrogen. So I'm going to, which one should I do? Maybe I'll just go ahead and go up here. There's a hydrogen here. Yeah, there's an sp3. This would be sigma, right?
Yeah.
And then we have 2 lone pairs, right? 1 lone pair sticking out, 1 lone pair sticking in these sp3 orbitals here. Then we're done.
So when you said we don't show the whole thing?
Well, I'm not going to ask you to tilt this and show me the side view. Actually, I have in the past. I've asked people to show me the side view of this, but I asked them just to show me the side view of this part, not the whole molecule tilted. So if you were to show the side view, you have to tilt this 90. And this part sticks out and this part sticks in. And it gets all messy.
So the top view would be fine.
Yeah, top view's fine. If it were simpler, then I'd ask you to show the side view too. But in this case, I wouldn't ask you to draw the side view of this because it's just too much.
So in the test, the whole thing, that's what you want, right?
No, and then also I want the orbital energy level diagrams, right?
Oh, yeah.
Yeah, and so that's not hard. I mean, I'm not gonna say, okay, draw hydrogen's orbital energy. If you draw it, that's 1s, right?
Yes.
And I gotta spin up here, this one. And then carbon comes in. Carbon's coming in with a sp3 electron. Spin down. Okay, so this is from hydrogen's perspective. Okay, carbon comes in with sp3, right? And then we go to this carbon here. You know, usually I'd just ask you the central atoms. I'm not going to ask you all the terminal atoms, otherwise it becomes a bit much. And so here, if I do this carbon here, you know, what do we have? We got sp3, right? And so the carbon sp3, we got 4 of these. And then I screwed up the spins because this one I had spin down, okay? This one's spin up. This one, where's my other one here? Spin up. Spin up. And so we have a hydrogen S coming in here. And then what else? We have another hydrogen S coming in here. Another hydrogen S coming in here. And then a carbon sp2 coming in here. Do you want me to finish it or? No. Okay, you got it?
I want to show you from color.
It would be nice, if you don't have a multicolored pen, then I'd just make the line look different. You know?
How can you read that?
All right, something, just do something so it looks different.
Or we can draw like arrows pointing to them.
Or draw arrows pointing to it, yeah. Just make it look different.
Professor, were you going to show, can you show the hybrid, the one that I told you with the dashed line?
Yes, I'm going to show it right now.
Thank you.
In fact, can I erase it?
Yeah.
Oh, the resonance. The resonance. I used the terms.
All right, now, that's acetic acid. What else do we want to know? Okay, we draw out kind of the electron density here, right? And we see how the electron cloud is distributed. But what else we want to do is we want to determine formal charge and oxidation state to give us a little bit more insight into acetic acid. And so let's do both. Now, I often ask, what is the hydrogen-carbon-hydrogen bond angle here? Okay, good. A lot of people will say 90, and then I ask the carbon-carbon-oxygen bond angle, 180. 180.
Wait, which one?
This one, the carbon-carbon-oxygen bond angle, lots of people will say 180 because I drew it as 180. They're right, it is 180, but that's not what I want. Yeah, I want the actual angle, not the one I drew.
120, right?
Yeah, it should be 120, roughly. All right, so we kind of have the electron cloud, how the electron cloud is, but is that electron cloud symmetric, you know, evenly shared? No, and so we look at other things. There are 3 ways for determining or analyzing these. The 3 ways are, you know, oxidation state is 1, 2, formal charge, and 3, polarity, bond polarity. And that gives us a picture of what's happening with the electron density. So let's take a look at first the formal charges. Are there any formal charges here? No, all the formal charges are 0.
Did not.
No. Usually for 0 formal charges we don't show them. We just show non-zero formal charges. And so none of the formal charges. And then we go to oxidation state. What are the oxidation state?
Carbon +4.
Actually, I'm going to show all the formal charges because we need to compare.
With 3 carbon.
We circle the formal charges. Now carbon is, this carbon is, what is it again?
Minus
Plus 4?
Minus 3.
Minus 3.
Wait,
This carbon is minus 3.
We will take all.
What is this hydrogen?
plus one.
Oh, okay, so basically this carbon took electrons from these 3 hydrogens but didn't take one from this carbon, right? And so which one is correct? Is the green charge correct or the red charge correct?
you can have a purple.
It depends.
Well, tell me, is it black and white or is it somewhere between? It's somewhere between, right? And in this case, carbon hydrogen, the difference in electronegativity is less than 0.5. The difference in electronegativity, carbon's at 2.4. Do you know where hydrogen is? 2.1. Hydrogen is between boron and carbon in terms of electronegativity. And so it's kind of in the middle of the periodic table. And so it's a pretty even match here. And so the last thing is we show the bond polarities. Bond polarities is something kind of in the middle between these. And here we show that using delta plus and delta minus. This charge is not 0, it's not plus 1, it's somewhere between. We call it delta plus. I don't know if that's visible. Okay. Okay, I ran out of colors, but let's go with color blue. So this is delta plus, but it's very small. Delta plus, delta minus on the oxygen. And so somewhere between, right?
We can also do the arrow.
We can do the arrows too. It's fine. The arrows would be written like this, but the arrows are very small. And so we say this is negligible. This dipole is negligible. That way, we can come up with a rule. The rule is hydrocarbons are nonpolar, no matter what their shape is. Hydrocarbons are nonpolar because the bonds are nonpolar. It need not be symmetric. It could be totally asymmetric, but we wouldn't expect a hydrocarbon to be polar because the carbon-hydrogen bond, yeah, it's not. Even if it's asymmetric, it's not. This is asymmetric, and it's not going to generate much of a bond dipole.
Why did you say it's negligible?
Because they're too close to each other. It's pretty much a tie, Carbon-carbon is going to be a tie. Okay, so let's go on. What's the oxidation state of this carbon?
Plus 3.
Plus 3. And so is the charge on this carbon plus 3 or 0? Somewhere in between. Now this carbon here is, well, it's going to lose electron density to who? It's losing electron density. This oxygen is -2. This oxygen is -2. And so it's losing electron density to these 2 oxygens. It's not losing 4 electrons. Where's that extra electron coming from? From hydrogen, which is a +1. And so in this case here, there's significant positive charge buildup on this carbon. And so what we say here is, when we're thinking about redox properties, this is the atom that stands out here. Is oxygen is pretty electronegative. It's going to want -2. It's the second most electronegative element. And so oxygens we don't expect to be very reactive. And so as far as redox, I'd expect this to be electron poor. However, next door to this is electron rich. So it's kind of interesting in the sense that, in one sense you don't expect this acid to burn, acetic acid, because electron poor. In the other sense, you expect it to burn because electron rich. So does acetic acid burn? It turns out, yes, acetic acid burns. Have you ever heard of the tricarboxylic acid cycle?
No.
No. In biology, when you look at the metabolic cycle, acetic acid pops in there. People eat vinegar. They don't die. They actually get energy from it. But some people drink this stuff. Okay. Well, anyway, so this is how we're analyzing this, and then this is delta minus, this is delta minus, and then this is going to be delta plus. Except this delta plus is going to be much bigger than that delta plus. So if I were a base, like water, which hydrogen would I be more attracted to? Now the base is, the part of the base that's going to be attracted, base is this, this oxygen has a -2, but it's also delta minus here. It's going to be attracted to this hydrogen here. And so by using, our electron counting methods, we can kind of get an idea of how the electron cloud is distributed, and so in the sense, we saw how we distributed the electron cloud using the orbitals, and then we see how it's going to be polarized. That is, the electron cloud is not going to look symmetric here. The electron cloud is being pulled towards oxygen. And so we have an sp2 sigma bond, well, the electron cloud is being pulled to oxygen, and a pp pi bond. And in the pp pi bond, the electron cloud is being pulled towards oxygen. And the same thing here. This sp3 sigma bond, the electron cloud is being polarized like this.
Other way around.
Oh, thanks. Yeah, other way around. Here. It's being polarized like this. Is it completely plucked off? No, there's still, hydrogen still is holding on. Barely. To the electron density, barely. But still. And so if it completely let go, it'd be ionic, right? And so this is called a polar covalent bond. So if I were a water molecule, I wouldn't be attracted to these hydrogens at all, right? I would be much more attracted to this hydrogen. And you think, how does the water pull off the proton? How the water pulls off the proton, there's got to be some kind of electrical attraction here to tug the proton off, or a big collision to knock the proton off. And so, in organic chemistry, we showed that like this. We showed that these are going to pull on the hydrogen line. The base comes in. They call this attack. The base comes in and attacks the acid. Pluck off that proton, leaving these electrons behind. And so if water is successful, and it is partially successful because acetic acid is a weak electrolyte. Weak electrolytes partially hydrolyze in water. And so they partially hydrolyze. What forms? Let's see what forms from this. Well, what forms is going to be acetate. And so let's go ahead and draw the structure for acetate. And hydronium. Both of these are ions, so technically we are supposed to draw the square brackets around it. All right, now let's take a look at acetate. When you look at acetate, and what's changed? Well, what's changed is the formal charge has changed. Pretty much all the oxidation states are the same. The only change in formal charge is now this oxygen is -1. Like that. But is this oxygen really -1? It's not between -1 and -2. It's between -1 and 0. How do I know it's between -1 and 0?
Resonance.
Because of resonance. Take a look.
Resonance.
In fact, because of resonance,
Yeah, that's fine.
I could rearrange the electron cloud to have this oxygen minus, right? Bump these electrons down here, pop these electrons out. You get this. But it's neither one of these because, you know, it should be the hybrid. And so what will the hybrid look like? Let's draw the hybrid out for this. And so the hybrid is, this is no problem. You know, this stays the same, this stays the same, and then one bond on each oxygen stays the same. But the double bond is, what do we call it? Yeah, the double bond is spread out over both. And so this is the dash, right? And then you see 2 lone pairs are always fixed on each oxygen. And so these are called localized, like this. But 1 lone pair delocalizes over both oxygens. And to show that being delocalized or spread out, I draw like, you know, spreading out the fog or the mist or the electron cloud or the water. And so this is why it's drawn differently, because that's not a localized lone pair there or localized here. It's actually all spread out. Right? And so this is the hybrid structure. What are the formal charges now? Minus a half, minus a half, and the bonds are not single double, they're 1.5 bond, 1.5 bond. And so the electron cloud delocalizes. Do you see that? It spreads out. Spreads out. That's acetic acid. Let's compare this to another oxy acid. Okay, the next oxy acid we're going to compare is something called trifluoro. Rather than hydrogens there, let's put in fluorines here. It's going to be trifluoroacetic acid. Take a look at what that does to this carbon here. Remember this carbon was -3, but now look at the carbon. What is the carbon here? +3. Do you see the huge change in how the electron cloud is now distributed? This is a huge change because before the electron cloud was, you know, there's quite a lot around carbon, but now it's being sucked away. Sucked away by fluorines. Fluorines are pulling the electron cloud away, sucking electron density from carbon. Now that's going to have an impact on this other carbon because this other carbon is getting electron cloud sucked away from the 2 oxygens, right? But now not only is it getting electron cloud sucked away from the 2 oxygens, but the other oxygen is trying to suck electron density away too. But now both of these are, well, this one's still +3. But can you see the huge difference in electron density distribution? Okay, this is called induction, or the inductive effect. The inductive effect is the fluorines suck electron density, Normally, carbon-carbon is a tie, right? But now this carbon's trying to suck electron density away.
How is this?
Should be a tie. But before, compared to a normal carbon it would be a tie. But now, or it could be still a tie. And then we got this, and the net result is this. Even though this carbon's pretty far away from this hydrogen, you know, it's making everything move to the fluorines, which means that this hydrogen becomes much more polar. So that's inductive effect. Now, the bond energy is about the same, therefore, which one's a better acid? Trifluoroacetic acid or acetic acid? Trifluoro. This is a much stronger acid. It's a much stronger acid because it's much more polar, the bond.
Why is that arrow pointing from fluorine to carbon? Like
Because it's wrong. Thanks.
What about carbon to oxygen? Why is it? Should be the other way.
But, you know, all this is trying to show is this. The inductive effect is before it was like this, right? But now with this here, it's either tie or it's much less so. And so either it's grown smaller, you know, because now carbon's pulling more, or it could actually be a tie, or it could actually be reversed, depending on how much electron cloud got sucked away. Do you see? It's not going to be the same as before. And so this has changed. To show it's not going to be the same as before, we show it like this, to show everything being pulled away to the fluorines. Okay. And so if you drew it to oxygen, that's okay. Yeah. This was clearly a mistake here. This should go to the fluorine. I drew it this way because this is called the inductive effect, this electron withdrawing. Inductive effect. And the inductive effect is going to make this a better acid.
Since this point on, is this for the final or is this for the last?
This is for the final.
That's for.
Yeah.
So we don't.
Right, you don't need to know this for Thursday. Okay, now we add water to this, you know, and we hydrolyze this. And what we're going to see is this. We're going to get the trifluoroacetate ion. The trifluoroacetate ion is going to have how many resonance forms? Two. So we can show those two here. And then the resonance hybrid. When we show the resonance hybrid looks very similar to what we just drew for acetate. And we show the formal charge. The formal charge should be negative 1/2, negative 1/2. But, you know, think about this though. Is it really negative 1/2? No, because of the inductive effect. Because of the inductive effect, we expect more electron density to be sucked towards the fluorine, which is actually going to lower the negative charge on this. And so these two negative 1/2 are not equivalent. This one is going to be smaller, right, than this because of the fluorines, because of the inductive effect.
And therefore it's a better acid.
No. Okay, now what makes a good base? These are the conjugate base. These are the bases here. They want protons. So what makes a stronger base? Having more negative charge or less negative charge? More negative charge, because an acid is H+. The more negative charge, the stronger it's going to pluck an H+, right? And so this turns out to be a weaker base. It's a weaker base. Why?
Because of the fluoride.
This is a weaker base. This is a stronger base. It's because of the negative charge density. The more negative charge density, the stronger the base. The less negative charge density, the weaker the base. And so in this case, this is a weaker base because of the...
Because the fluorides are stopping all the...
Yeah, because of the inductive effect. The inductive effect reduces the formal charge on the oxygens, making it a weaker base. In other words, the more we can delocalize the negative charge into the structure, the weaker the base. The weaker the base, the more stable it is. Now, powerful bases are unstable. You've got a lot of high charge density that needs to be taken care of. Okay. Next, let's take a look at ethanol. Is ethanol a good acid? No. Ethanol is a very, very weak acid. In fact, it's so weak, people don't really consider it an acid. However, it can act as an acid if you have a powerful enough base to come along to pluck off the proton. And so let's imagine ethanol. Oh, this is methanol. Ethanol should have more carbon, like this. So if we look at ethanol, a powerful base comes along. Which proton will it be attracted to? Which hydrogen?
The hydrogen next to the other.
Yeah, over here. This is why we say, you know, when we have an acid, you want to bond the hydrogen of the acid to the most electronegative element to create the biggest positive charge. Because if you have a strong base, it's pretty much going to ignore these because the positive charge buildup on these is negligible. Whereas this one's going to have more significant positive charge buildup. All right, now let's say I had, well, water's not going to be powerful enough to pluck it, but I need a strong base to come over here and pluck it. And so if I pluck off the hydrogen, well, based on polarity though, let's take a look at this versus this. And let's look at this based on polarity. Based on polarity, oxygen is a 3,5, hydrogen is 2,1. 3,5 versus 2,1. The difference is 1,4. Okay, 3,5, 2,1. The difference is 1,4. So shouldn't these be equal in acidity? Because the polarity is the same, the bond strength is the same. The polarity and the bond strength are the same, then aren't they equal? Well,
What else?
okay, we also have to look at a third factor, but before we look at the third factor, that's, you know, this is polarity oversimplified. Because these two carbons are not the same. The carbon up here versus the carbon down here are totally different. Can you see why? Even though they're carbon, and carbon should be a, what is carbon? 2,5, right? 2,4? Is it 2,4? 2,5? Something. This is why we need all the tools we can in analyzing this. But if you look at these two carbons, do these two carbons, are they both 2,5s? They're both the same? Or do they look different? They look totally different, don't they? You know, when I look at these two carbons, you know what I see? I see electron rich and I see electron poor. Do you see? Which one is electron rich? Yeah, this is electron rich, this is electron poor. You know, that makes a big difference in this bond here, right? Because of what effect? Inductive effect. You know, what's the oxidation state of this one? -1? And this one? +3. Big difference. Which means this one, actually, when I think about this, even though it looks the same, this one is not going to have as big of a delta plus as this one. This one has a much bigger delta plus because this carbon. And so, you know, this is why alcohols are not really acids. Alcohols are just alcohols with their own characteristic properties, whereas carboxylic acids are acidic. Right? Even though they both have the COH link. It's this double bonded oxygen changes the electron cloud in carbon significantly, resulting in sucking of electron density away from this hydrogen. And so based on that, I would expect acetic acid to be a much better acid, right?
Choosing more acid?
Hmm?
Choosing more acid?
Acetic acid is a much better acid than ethanol. In fact, ethanol is so weak. But ethanol,
What's the carbon negative one on top?
I don't know. Let's check it. It's 2, 4, 5. It's supposed to have 4, so it has an extra electron, so it'd be -1. Do you see the electron count? Carbon-carbon split in half. And so that's 1, 2, 3, 4, 5, and none of these. So oxygen wins. It's a winner take all. You know, even though it's winner take all, we're assuming 100% ionic, these numbers are very useful, you know, in comparing. And like here, this is how we compare. -1 + 3. Very useful.
What's the question?
Accuracy,
How do you know,
regardless.
like, when to use oxygen state or formation?
We use everything. Everything available we use to try to understand. Because remember, at the beginning, the whole purpose was to try to correlate structure, composition structure with properties. And so whatever tool we have to understand structure, we're going to use to try to understand properties.
So because carbon on top is supposed to be +4, but it has 5 as an extra
Not +4, it's supposed to have 4 electrons.
4 electrons.
Yeah.
And then it has 5.
Yeah, so it's -1. Yeah. Which one is going to be useful? You know, I don't know. Was formal charge useful at all? Is formal charge useful at all? Worthless. Oxidation state? Useful. So use it. Polarity? Useful. We use it. You know. Do you see how we're digging deeper? In Chem 4, you always call this 2,5, but these two 2,5s aren't the same, right? In Chem 4, I asked, do these have the same electronegativity? True or false? Does fluorine and fluoride have the same electronegativity? A lot of people will say yes, because it's 4O. And it's F, right? A lot of people will say this is the same as this. It's a 4O, this is a 4O. But not at all, right? Fluorine's a 4O, fluoride is a negative, you know. Fluoride doesn't want anything. Fluoride's not even on the chart because it's off the charts. So, and so the electronegativity chart you've been given is the bare bones, the elementary school version of the electronegativity chart, right? There are much more advanced electronegativity charts that look at, you know, the changes in the bonding environment which will change the electronegativity. And they've done some calculations to come up with some simple numbers that you can use to determine this. But we don't have to use the fancy electronegativity charts. Instead, what we're going to do is we're going to try to analyze it using oxidation states to try to come up with some kind of reasonable answer. And so based on polarity, which one's a stronger acid? Acetic acid. Based on bond strength, which one's a stronger acid? They're the same. And then what's the third factor we look at? No, the third factor. The stability of the conjugate base. And so let's look at that last factor here.
Stability of the conjugate base. So we're returning it.
Okay, so let's take a look at the conjugate base for this one. If we lose the H plus, let's say, I'll just do this as a simple dissociation. If we lose the H plus here, we generate this structure. What's changed? Have the oxidation states changed? Have the oxidation states changed? Do the oxidation states, can you do them in your head? Have the oxidation states changed? No. What's changed? Oxygen's formal charge is now minus. That's it. That's the only thing that's changed, right? All right, let's take a look at acetic acid. Acetic acid is going to form acetate, which we've already drawn.
Can you show an example why oxygen's formal charge is negative?
It's right there.
No, I don't know.
Oh,
What is it, dude?
why this is negative?
Yeah, why?
It's winner take all. So who wins? Carbon versus oxygen, who wins? Why does oxygen win? It's more electronegative always wins the tug of war. So winner takes all. Now count how many electrons oxygen has now. 8. Do you see it? 2 for the bond. 1, 2, 3, 4, 5, 6, 7, 8. How many valence electrons does oxygen normally have? 6. So it has 2 extra electrons. 2 extra electrons.
We're doing formal charge.
Oh, so that's oxidation state. Okay. Okay. Formal charge assumes winner take all? No, formal charge assumes 50-50. Everything's 50-50. No matter how strong or how weak, everything is 50-50, right? I think that's how communist countries are supposed to work. Everything was distributed evenly, right? But it didn't turn out that way, right? Anyway, going back to this, if it's 50-50, then we split it. 1 electron to carbon, 1 electron to oxygen, which is a nice thought. And then we count how many does oxygen have? 1, 2, 3, 4, 5, 6, 7. -1.
But then the oxidation state would be
-2. The oxidation state didn't change. So -2 to -2. So was oxidation state worth anything? It's worthless. It didn't tell us anything, right? It's the same, didn't change. But the chemical properties sure did change. It must be correlated with something else. All right, now looking at these two, which one is a stronger base? They look the same, don't they? Oxygen minus 1, oxygen minus 1, they're both going to be attracted to H+. So which one is going to have a stronger attraction to an H+? Oxygen minus 1 versus oxygen minus 1? They're a tie, right? Oxygen minus 1, oxygen minus 1. These two bases must be the same strength. Yes? No.
Wouldn't it be the
That
one,
one goes
the one on the bottom?
Oh, is it the one on the bottom because of the inductive effect? Is that it? Because this was minus 1 here, this is plus 3. And so that's going to suck more of the electron cloud away. Yes? Is it because of the inductive effect? It sucks a little bit of the electron cloud away. Or is it because of resonance delocalization? It's because of resonance. There's a huge difference between these two. It's not because of the inductive. It's a little bit to do. Inductive effect is part of it. But the main thing is resonance delocalization. What was resonance delocalization? Yeah, so what is a hybrid? Can you draw the hybrid without drawing the other resonance strong? Yeah, we already did this one a bunch of times. And what does the... Yeah, what's the formal charge now? Minus a half. Minus a half. And so the biggest thing sucking the negative charge density isn't the inductive. This is going to pull electron density here. The biggest thing is it's going to delocalize the electron cloud over both of these bonds. And so it's going to drop significantly. Now we have the inductive effect because it's pulling here, but remember this carbon is still electron rich, but still compared to that. Okay, and so this is called delocalized. How about this? Can I just kind of suck the electron density into the carbon here? No. Can I delocalize as a negative charge over these bonds here? No, not at all. This is called localized. And so this turns out to be, ethoxide is a powerful base. A strong base. Acetate is a very weak base. Very weak base.
That's because of the resonance.
Yes, right. So there are two things when we look at the stability of the conjugate base. The most important thing is if you could resonance delocalize. If you can delocalize electron cloud, and in other words, in organic chemistry, this is the way you predict which base is stronger. The more resonance forms you can draw, the weaker the base. Yeah. Because the more resonance forms you can draw, the more spread out the electron cloud is, and the more delocalized that electron cloud is. And so that's the rule in organic chemistry. And then you start looking for things like inductive, like this, right? And other things. Inductive is next, but number one is resonance delocalization. And so when we have localized charge like this, it's bad. It could be also.
Which acid is stronger?
Which acid is stronger? Acetic acid is stronger than ethanol. Acetic acid is stronger than ethanol primarily because of the stability of the conjugate base. That's the primary. It's slightly more polar than ethanol, right? And it has some inductive effect that helps stabilize it. But the primary reason that acetic acid is thought to be a much stronger acid than ethanol is because of the stability of the conjugate base. Resonance delocalization. Are we already out of time?
I don't know.
Wow, I gotta talk faster. No, actually, this stuff, this chapter 16 stuff, since this is an application of chapter 10 and 11, I mean, and this is an important application because if you can continue on in chemistry, you're going to have to do a lot of this kind of analysis, especially in organic chemistry. And so, you know, this is good to spend time on. Whereas the chapter 12 and chapter 13 stuff is a little bit here, a little bit there you use.
Do we still cover 2 more chapters in the final?
Yeah.
2 more chapters?
But not complete, you know. I'm going to skip some stuff in the as I condense some things, so it's not as in depth. But the homework assignment's going to be smaller. I don't know if I posted. Did I post it yet?
We only have chapters
No.
left.
Yeah, those are going to be smaller. All right.